Today we're going to be talking about continuity and whether a function is continuous or not. Okay? Now, the main idea behind continuity is that if I can draw the graph without having to pick up my pencil, right? Something like this, no matter how crazy it looks, as long as it's a function, right? Then that function is continuous. So a continuous function can be drawn without picking up the pencil. Now this is a very non-mathematical definition. So what it means, again, mathematically, is that how there are no holes. If there was a hole here, I would have to pick up my pencil and then put it back down to draw it again. If there was a big gap here, so something like this, and I would have to pick up my pencil to draw it again, there would be another discontinuity. Or maybe there's some sort of an asymptote, a vertical asymptote. So if that was the case, something like that, to continue something like that, right? This would also be another discontinuity. So this function right here would be considered discontinuous. Now let's look at the mathematical definition of continuity. So again, a continuous function, I do not pick up my pencil in order to draw the function. And if a function is continuous, let's examine it point by point at some point A. So we are currently talking about continuity at x equals A. What do we have to know happens at x equals A? Well, the limit from the left-hand side, the limit as x approaches A from the left, going in this way, and the limit as x approaches A from the right, moving this way, must exist, so it can't be positive or negative infinity, and it has to be equal to f of A. So if I plug in A, it must give me an output. That's exactly the same as the limit. So these three criteria, they must exist and be equal in value. And that is how you know a function is continuous at the point x equals A. Now if A is any number here, any number on the number line, then you know that the function itself is continuous everywhere. So now let's talk about the three types of discontinuous functions. The first type looks something like what we've been dealing with before, where f of x could be something, it could be a piecewise, where you have a graph that essentially looks like a line, except at x equals 2, there's some sort of a hole. So a graph like this factors into x minus 2, x plus 1. So it'll look like the graph x plus 1, if this is 1, except at 2, there's going to be a hole, because it's not in the domain. So the function is this, as long as x is not 2, and at x equals 2, it looks like the output is 1. So this is what we call a removable discontinuity. Because with one point, we can basically remove the discontinuity. With one point. It could mean moving this point, or if this point wasn't even here, and we just had this top function, it would still be considered a removable discontinuity. Basically when there's a hole. Right? So if they ask you to remove the discontinuity, you might be able to change this value. Instead of an output of 1, we would need to give it an output of 3. right? Because when you plug in 2, 2 plus 1, it should give you that 3. That would be how to remove the discontinuity. Moving on, the next kind of discontinuity looks like this function, and I don't know if you remember what this function looks like. It's the integer function, where here's 1, 2, 3. Let's start with that. Whatever value you plug in for x, and you can plug in any number you want. So if I were to plug in 0, it would round down to the nearest integer. If I plug in 0.5, it would still round down to the nearest integer. If I plug in 1.9999999, it would still round down to the nearest integer. Except when I plug in 1, it will give me an output of 1. 1.1, 1.4, 1.5 would still round down to an output of 1. Except at 2, again, 1.99999 will still output 1 because it rounds down to 1. At 2, it will now jump up to 2 because 2 is the next integer. So it looks like a little step function, something that looks like this. And integers, remember, include negatives. This kind of a discontinuity, oops, this should be open, is what we call a jump discontinuity. Because basically the limit from the left is not equal to the limit from the right. They exist, but they're not equal. Right? So from the left and from the right, they're not equal. In this case, the limit from the left and from the right are equal, but it's not equal to f of a. Okay? So this is what we call a jump discontinuity. Now let's take a look at this example at x equals 2. So the limit of f of x as x approaches 2 from the left, that exists and it's equal to 1. Right? The limit as x approaches 2 from the right is equal to 2. So as x approaches 2 from the right-hand side, the output is 2. Now f of 2 also exists, and that happens to be equal to 2. Now if this is the case, and you have something that looks like this, right? Where the limit, a one-sided limit, is equal to the actual output at that point A. Then we call this continuous from the right. Now that looks like one word. Continuous from the right. Right? Because of this, because the limit from the right-hand side is equal to the output at that point A. So this is continuous from the right. If this happened to be equal to the limit from the left, of course we would call it continuous from the left. Now the last kind of discontinuity is kind of like our maybe f of x is equal to 1 over x. Something that looks like this, right? If there is an asymptote here and the limit, if we call this A, the limit from the right, the limit from the left is either does not exist, positive infinity or negative infinity, we call it an infinite discontinuity. Continuity. Now if you notice, this is literally the only type of removable discontinuity. These two are not removable. So now let's just do one example. Let me finish writing this. Oh gosh.